but I'm back now. I'll start the recording in case it's useful for me to go back later and review it. But if you can share your screen and just show me, and I know it may be on paper so that it, yeah, if there's a way you could scan it or take a picture and share it or post it, then I'll be able to better follow what you're saying. But so far it sounded not very different from what you talked about last time, which I think is in generally a good approach. You were, I think, moving it to a basis that I thought was like harder to measure, like harder to convert back to 0 and 1, which doesn't make it wrong. It's just I felt it was like other extra steps. And so if you can show what your teacher's feedback was, maybe we can figure out if there's something deeper, whether we basically got to the essence of the problem.
Okay. So I will be able to share my screen now. So let me go ahead and do that. So
Sure.
in this case, I pretty much showed my problem as if I was trying to figure out I mean, of course, but right here, I don't think it had anything to do with the answer. She ended up saying it was all good. The only thing that she really highlighted was this part. This part right here is the thing I believe she highlighted, and I'm not
sure
where I got that wrong because I was but
no, I just wanted to like state for myself and check in with you. It looks like XYZ was the original bits, which are either summed to 0 or 2. And instead you converted it, you did substitution of variables where you had new bits, classical bit labels, A, B, and C, that converted the 0 versus 2 case to the 1 versus 3 case. Is that right? You froze up.
Yeah. So I was thinking that. Wait, what?
Sorry, I thought you froze up for a minute, but yeah, your image is frozen. I think maybe there's a. Let me do an internet speed test, make sure it's not a problem on my end.
That because A plus A modular.
Sorry, Caleb, you're cutting in and out, and I think my internet connection is plenty fast. So is there any chance that it's a Wi-Fi problem on your end?
Did I was I out of the meeting for a moment?
You were there, but your image was frozen, and then your sound like cut out for a long period of time. So I double checked my Wi-Fi. I think it's pretty fast. I just wanted to ask, is there any chance that it could be the internet connection on your end?
Maybe I'm not fully sure if that would have been the problem, but maybe that could have been the issue or something. But
well, it's much better now. So
yeah. So let's see. So
sorry I missed your explanation. So the last thing I remember saying to you was that you had the original bit labels XYZ, and you wanted to distinguish between the two cases of their sum being 0 versus their sum being 2. And you appear to have substituted variables to be ABC, and the two cases are also translated to be the sum is 1 versus 3. So is that correct?
I was thinking that was correct. Because if you had A plus B plus C equals 1, then either A or B or C equals 1 and the rest equals 0. In that case, you'd have 0 modulo plus 0 modulo plus 1, or 0 modulo plus 1 modulo plus 0. The order really doesn't matter because I believe you would have always gotten 1. And in that case, you would have won the game. For A plus B plus C equals 3, I thought that was also correct because if you had one module, there's only like one case where that's true, 1 plus 1 plus 1. So I was thinking if you had one module plus 1 module plus 1, it would equal 1. But in the way that the teacher ended up highlighting this, she didn't really give a specific comment. She just highlighted it, and I believe when she highlights it, it's mostly something that you got wrong. But I believe when I did that, I should have been able to. I think if you did one module plus one module plus one, I don't think it would have ended up in 0. But could that have been possible at all? Or
Yeah, well, I'm not following the definition, so I need to know the definitions of A, B, and C. So the other things that you say on this page are not controversial, but I guess can you scroll further up to where you define A, B, C?
so I don't think
Yeah.
yeah, I don't really think the fine and see either of my internet, because I just got noticed that my internet connection
Okay, yeah,
is
you are
unstable,
cutting out again. Do you see me like freeze up? Your image is frozen for me right now, and then some of your sound is getting through.
that may be a problem, but I don't see you freezing up. It could be my end, because I know at least that I just got that notice that my internet connection is unstable.
Let's stop both our videos, because that's just extra load on the camera, and then it's just the screen share and the audio, which is much lower bandwidth, and hopefully that will, whoever's, and it could be a problem on Zoom's end as well. So whoever whatever link along the way is the weak link, hopefully less camera, less bandwidth will stress it less. Are you still there, Caleb?
Yep, I'm still there.
Okay, great. So far it's improving. So can you scroll to the very first page? I think that's the missing definition. So so let's see, so A's and B's and C's now have a subscript. Can you tell me what the subscript means? Is that like, you're saying that that's the case when A equals 0, like Alice receives a 0, B0 is when Bob receives a 0, and C0 is when Charlie receives a 0? Is that?
Yeah. So what I was trying to say in that case is that A0 is sort of the strategy for when Alice receives a 0. B0 is the strategy for Bob when Bob receives 0, and C0 is the strategy for when Charlie, or the output, really, more so the output for the strategies of each player when they get a 0-1, and the subscript represents the strategy each for their respective values. And in that case, the A plus B plus C is technically an output bit. So in that case, Alice, Bob, and Charlie can only output 0 or 1, and based on that, they can either win or lose. But
right. So I guess the first thing to note is that you were given a promise. This is a promise problem where it doesn't have to win on all inputs. You're restricted to the inputs that you've given, which is that 2 out of the 3 bits are 1, or none of them are 1. They're all 0. And so later, whenever you try to handle cases where ABC equals 1 or 3, you're promised that will never happen. So that's probably one thing that your teacher was trying to draw your attention to by highlighting it. And then another is that this next set of 3 equations ends with 0 equals 1, which is usually not what you want. So I would have to, I guess, I'm not really sure what you mean by that, because A and B and C without subscripts are random variables which take on values depending on which case of the input that you get. And I wouldn't expect to add them together modulo 2 in any case. It's yeah, I mean, there might be some game theoretic reason why you want to consider all the cases of all possible universes of the input, but
so I was thinking, at least for the modulo 2, I know there was a similar example in which she applied the CHSH gain, and when she she proved it, she pretty much added all of the values up together. The left was added by modulo 2. But the problem is I didn't know what she did for the right side. I know in that case, the CHSH game is based on the idea that Alice and Bob are given either 0 or 1, and that they have to find the best possible strategy for success. The quantum strategy in that case would win 85% of the time, which is better than the certified 75% of the time. But essentially in that case, you would add up all of the left side equations by modulo 2, and for x and y, it's pretty much an and statement. So you'd either get like a 0 modulo 2 b 0 equals 0, a 0 modulo 2 b 1 equals 0, a 1 modulo 2 b 0 equals 0, and a 1 modulo b 1 equals 1. I was thinking originally that you would have to use the operators from each side, but if you did 1 and a 0 and a 0 and 0, you would get pretty much 0. But I know in that example, she said it was 1. So I was thinking if you did that, the answer would have had to be modulo 2 operators in that case. So what I was thinking...
well, hold on. So, I mean, yeah, if you can actually show the CHSH example that you're talking about, but I mean, given here, are you rearranging the terms so that all the zeros are at the beginning and all the ones are at the end? Like on this second line?
So for this second line, I'm trying to I think this is the line you're talking about, the one. Oh, okay. So in this case, I'm pretty much just rearranging everything because the way the teacher phrased it was that if you had a number added by itself, you're pretty much going to get 2 times that number. But a modulo 2 operator requires that if the number is even, it's 0. So if a modulo 2a, if a mod 0, a sub 0 modulo 2a sub 0 is going to be 0, b sub 0 modulo 2 b sub 0 0, and so on, they all end up adding up to be 0. So that is sort of the proof in a sense that that is not true.
Well, I mean,
I will go ahead and pull up.
Yeah, I mean, be more explicit and say that this O plus notation that you're using, we can define it as plus addition under modulo 2, or, cyclic group order 2, and where, 0, O plus 0, and also 1, O plus 1 are 0. And then the only cases that you get a 1 are these other cases, which, looks pretty much like XOR, exclusive OR. So if you're trying to add up all the one sides of the equations, here, and then and if each individual one is equal modulo 2 to the sum on the right, then I can see why you would expect to just, add up all of one side and then add up all of the other. I'm not sure what it gets you to do that, but let me just check briefly that you have 2 A zeros, you have 2 B zeros, you have 2 C zeros. Okay, so I guess like two of everything.
So here's I know what
I'm gonna call at the moment, so I'll be done in an hour.
Okay, so I know that for the input, this is the SH game that you provided, and I think in the homework itself, the teacher said that it would have to be something that is modulo, that it would be specifically modulo 2 operator, where specifically 1 plus 1 modulo 2 1 would be 0 in a sense. So, and that 0 modulo 2 1 is 1, and 1 modulo 2 0 is 1. So that's at least what I think she was referring to. For the input and output for Alice and Bob, I know that the input for X, like this was pretty much, the first page is pretty much what she said was the CHS game. And the way she did it, she said like A, X, and B, Y denote outputs that Alice and Bob gave on inputs X and Y. She provided the winning conditions, and she pretty much added all the values up together. I realized that if you added all the values together, you would get 3 on the right side equation, and modulo 2 operators cannot do that. And thus you'd need only one, you'd have to have only one equation where everything would sort of work. But I know based on the input she gave, I know at least that if I did modulo 2 operators, this would work. If I try to do, or if I try to do it based on the respective operators of the right hand equation, this is pretty much an indicators that at least one equation cannot be satisfied, so your probability of winning is less than or equal to 3/4. And any sort of other extra strategy like probability or any sort of classical strategy from here on out would fail. So
Yeah, well, okay, well, let's pause here. So A, B, and C are the outputs of Alice, Bob, Charlie. X, Y, Z are the inputs. And oh, okay, so she's using this strategy to show that she's trying to show that no classical strategy will win 100% of the time. That's not my interpretation of to me, this doesn't prove that no classical strategy will win, but maybe it's equivalent. Like I would show,
I think I saw like a problem like this on extra examples, and I think there were extra proofs for it. Like you would also have to prove that probabilistically, if you just said like take everyone and flip a coin, would you get better chances? One proof was like the probability chances will only win as best, will only have the best chances as the best possible classical strategy. The other went ahead and directly proved that no, that's false. And I think there was one more in which they tried to use summation, but they got the same result, that you'd only win 3/4 of the time. I know at least for that case, the teacher was satisfied with this sort of modulo 2 addition. But yeah, that's pretty much.
Okay, well, now I understand why you were doing this way. And I'd have to think more about like why this is convincing, because that's a pretty strong statement saying that no classical strategy can win. But for me, I was going to do something much simpler, which is to like give a classical strategy that wins 3/4 of the time, which is just always guess one, or to but I think that's maybe the question was asking for something stronger than that. So I'll bring up the one PDF that I have. Yeah, the question just says, show that the best possible classical strategy wins this game with probability 3/4. So even showing that it's the best possible strategy would be kind of hard, but that's different than what the slide's saying, than what you're trying to do. But anyway, let's continue, because maybe it's not worth spending so much time on so much time on this part, but I guess I will say the ABC equals 1 plus ABC equals 3. So those are the outputs that the players give. And then, yeah, if you remember the circuit we drew last time, where the inputs were on 3 lines, the GHZ state was on another 3 lines, and then their outputs were on another 3 lines. So you could call that X, Y, and Z, then the GHZ state, and then ABC.
So yeah, sorry.
Yeah, and then I mean, I think your key step was the controlled on, one of the bits, or on each of the bits, flipping the, applying the S gate, the square root of Z gate. I don't remember. Was your solution to apply it to the GHZ or some other state?
I believe the solution was that I applied the controlled S gate to the GHZ state. Then I applied Hadamard's 3 times, and then I applied the C naught gate, or pretty much the controlled X gate, to A, B, and C based on the results from the for after measuring, essentially. But I'm probably just apply
Yeah,
but
it's okay. I took a screenshot, but do you mind redrawing your solution on Zoom annotation?
yeah, sure. So essentially I'm gonna just pretty much open up a new tab sort of for this to make it easier. But
Sure.
let's say I have probably better to just use lines. So let's say I have this sort of state. It's going to be pretty much 9 qubits. The only qubits that really will matter are kind of, well, all qubits sort of matter for, there's going to be, I think we both agree that there's going to be some qubits that represent the inputs, some qubits that represent the outputs, and some qubits that represent measuring to the outputs. So as kind of agreed, this would be something like, this would be X, this would be Y, this would be Z, this would be, all of this would be sort of the GHZ state. Then we have A, B, and C. So we pretty much get the GHZ state by Hadamard, control not, control not. So this, I'm just going to say this little area right here is going to be where we apply the steps to get that GHZ state to be the GHZ state. From there, we apply controlled S gates. So based on what X is, sort of, it's kind of like we pretend that there's going to be also X states here for each input. So if say Alice gets a 1, we apply an X gate to X. Bob gets a 1. If Bob gets a 1, then we apply X gate to Y. If Charlie gets 1, then you apply Z. So this is going to be essentially an S, the controlled S afterwards to get S as S based on the inputs. And then we just sort of apply Hadamard's all around. So something like this, and like this. Then we would just apply Hadamard's to the GHZ state. So something like this. And from here, we would just simply apply controlled X gates to the output bits. So something like this. And this would get our results. This would get us our sort of state that produced the answers. What Alice, Bob, and Charlie would each individually input would be these inputs. So whatever Alice gets for when they measure their states, what Alice gets here, she's going to output what Bob gets. I'm going to denotate this by A. If this is what Bob gets, then this is going to be B. Then Bob outputs this, outputs the second to last qubit. Charlie outputs the very last qubit. The idea is, I was thinking about this more generally, but I realized that if I just thought about this individually, then we would get sort of the answer in a sense. So.
Okay. Yeah. Thanks for explaining that. So applying the S gate, control the S gate on GHZ, which initially is, this maximally entangled 0, plus 1, 1, 1. Let's say that X is 1, so controlled on it, you apply the S gate, which gives a phase. We can call it e to the I pi over 4, right? And then
I was thinking that was TS would just be pretty much I. So it's sort of like, I think 0 state, then plus the I times the 1 1 1 state. I was thinking, because S was the square root of the Z state, which is 1 0 1 negative 1. Take the square of that. That's 1 1 1 0 0 I. So that's what I was thinking.
Okay, you're right. That's a different gate. There's like a phase gate or a T gate, which is the phase I mentioned, e to the I pi over 4. So you're talking about e to the I pi over 2, which is just I. Yeah, that's right. Okay, so let's say X is 1, then or if any of them, any of X, Y, or Z is 1, and then a second one is 1 again. So then you add this other phase that effectively applies -1 phase. And then you're promised that only 2 out of the 3, only 2 S gates will be applied, not 3 of them. So you have this case here where it's 0 0 0 minus 1 1 1, or in the case, so this is 2 out of 3 are 1s, and then all 0s case would be the last one got clipped off, so type it again. Okay, and then you worked out the effect of applying Hadamard's on all 3 of the bits, and if it were just a single bit, Hadamard can distinguish between these 2 cases with opposite phase. So I guess it's like intuitively, are you expecting applying the Hadamard's to all three having a similar effect, like being able to distinguish between the 3 zeros minus 3 ones versus 3 zeros plus 3 ones? Or
So what I was thinking was that when we applied the Hadamard's, it's kind of automatically do it, because if, say, it's going to be all 000, if we don't apply the S gate, the S gate's is 000 plus 111, then I figured, then after calculation, I figured that you would always get like, you would get 1/2 of all states in which we would win. So in that case, it'd be like 000 state plus the 011 state. So something like this. Then we'd add the 101 state and the 111 state. So essentially, in that case, if there are no S gates applied, we would always get a winning result. But if we do apply the S gates, the minus actually changes things again, because in the last Hadamard's, some of the states end up canceling out. But in this case, some of the states that we originally removed would now stay. So instead, we would get 1/2 of the state 0, 0, 1, then 010, then 100, then 111. So I figured, after some simplification, I found that it was actually a little interesting thing, that if this is, then if we apply this individually to all players, say each player begins with the Hadamard state, like 1/√2, or just the plus state of like 1/√2 of 0 plus 1. Applying Hadamard's is like self-unitary in a sense. So applying Hadamard's to this would simply result, and I'll just do something like this. I think there's a tensor here, but pretty much after simplification, you just simply get the 0 state, which always measures to 0. So if there are no S gates, Alice, Bob, and Charlie will always measure 0. So they'll always just choose 000. So essentially, we have the effect that we don't even really need to apply Hadamard's in that case. We just say if the player gets 0, they choose 0. But I think we need that for entanglement. So from there, I figured that applying S gate, if you just apply S gate to the state, you do Hadamard's of 1/√2 of the 0 state plus I times the 1 state.
well, it would never just be, yeah, you would never just have the I phase, because you're promised that the S gate will be applied twice on this maximally entangled state. So I don't think you have to worry about how to handle Hadamard on the I phase. But
when I was originally sort of, sorry. Yeah, I was thinking when I was originally doing that, I was thinking, hey, if we evaluate this multiple times, then we would get I ended up getting some crazy number. But then I came to the same conclusion you did, that it's the same thing as just one player applying a Z gate, and that's pretty much getting the minus state. And if you apply Hadamard to the minus state, you get 1. So always, either all players will get the 0 state, or in the case that no one gets a 1. But if 2 players get a 1, then always 2 players will output a 0, while the other will output a 1. So I ended up figuring that out, I think. And I ended up getting mostly full points on that, except for in the problem set 3, she said, I think she highlighted the A plus B plus C equals 3 case. And I don't know if that is a mistake on her part or a mistake on my part. So I may need to clarify.
yeah, I think
on that sort of.
Yeah, my interpretation of that is that you can get a solution where A plus B plus C equals 1, and that's it. You don't need like a second case where it's equal to 3. Yeah, so
Okay. That probably, you're probably right there. Yeah, that may be the thing that she got me on, was that realistically the A plus B plus C equals 3, that's unnecessary, because no, there's never a case which all players apply a 1. So yeah. So in that case, I think, yeah, thank you for that clarification. So anyways, I was hoping that we could try and move on to the
the random number generation.
yeah, do you have that by chance, or do you want me to try and pull
I-
that for you?
Yeah, please send it over. I never received anything like that.
Okay. Okay. So let me see. So um okay. So no, that's let me see. So sorry about this. Give me a moment. I think. How do I? Oh. So hold on. I think did I there. So I'm gonna stop sharing for a moment just so that I can get what I need to get.
Sure.
So I believe let's see. Oops. So sorry. Just trying to find where I put the file. I believe.
I'm just rereading the last problem, so no worries.
Okay. All right, so sorry, give me a moment real quickly.
Yeah, no worries.
Alrighty. So sorry, I'm almost done. Sorry about that. I think I found it, but give me a moment. Okay, so I am going to try. Let me see what I can do, but okay, here. So I should have the file for you. So here, oh no, that's the wrong button. So I am going to, okay. So here, this is the project I was helping you do. So
Oh, great.
It's also in your hand.
Yeah, perfect. I agree with everything in the paragraph so far. So we explore all ways of generating randomness. Classical computers can't generate true randomness. The project aims to emphasize connection between probability and quantum information by exploring or investigating how to sample from different probability distributions. And so the distributions are uniform, Bernoulli, etc. And also with an open-ended component where you can choose your own probability distribution. So that sounds really cool. So the first questions are about the uniform distribution.
I think the one thing I was trying to do was I was trying to find probability distributions of interest. I think I found one that the teachers thought would be a plausible option. There was Benford's law, but I've been trying to look through them. I don't know which ones would be better. I think discrete Gaussian could be a potential probability distribution, but I'm not fully sure.
Yeah, any of these sound great. There's like other physics inspired ones like the Boltzmann distribution that's used in quantum annealing. That could be cool. I don't know Benford's law, so I will look it up.
Okay.
But yeah, it's definitely guided by your interest. I would think of your other interests outside of quantum computing or what you might want to apply quantum computing towards, since all computing is usually a tool for modeling. I mean, sometimes you can study it for itself. So you could just choose a distribution that's just unique, but also if you are interested in solving particular kinds of problems, then we can look for distributions inspired by those.
Okay. So
Okay, so your candidates are Benford's law and what was the other choice you mentioned?
I was thinking maybe a discrete Gaussian, but I'm not fully sure about that one.
Yeah, that's true. So I mean, because we use the computational basis or transformations of it, it would be, you would have to choose a discrete distribution. So that does limit your choices. It looks like discrete Gaussian is useful for differential privacy. Yeah, this looks cool. Okay, so instead of putting all the a quantum state, of n qubits into equal superposition, which would be the uniform case, you want to have the weights follow different distribution. So do you have any like other criteria? Like how are you thinking of discrete Gaussian versus other distributions?
I was trying to find ones that would be a little more simple in terms of applying the quantum superpositions in. So I want to try and write down a potential quantum superposition that would model the probability distribution. So Benford, I'm trying to figure out which one would be best applicable, not only one that like I can write that about a quantum superposition of, but also something that I can program using simple simple quantum circuits. So
Yeah, there is a precision component, like not all distributions, but there's a limit to how accurately you can model these distributions, with a finite number of gates or a finite set of gates. You don't have arbitrary like rotation precision on single qubits, usually, for example. So are there limits? Yeah, are there limits like that? Like what gate set are you allowed to use?
I believe mostly it has to be known gates at least. I was thinking of gates that apply arbitrary superpositions, such as pretty much Hadamard's gate and an RY rotation gates, pretty much those gates. So because Hadamard's has a fixed superposition, as a fixed amplitude, essentially, I'm trying to find essentially a probability distribution of interest that has an RY rotation gate that makes it a lot more simple to be applied to, essentially. So that's what I was at least thinking for.
Yeah, usually it's I mean, you can compute anything to like arbitrary precision if you're allowed, exponential number of gates. If your circuit is like exponential in size relative to the number of input bits. So, and we can make reasonable assumptions that that's not what your teacher intends. And also that, well, we can look at the examples of like the binomial distribution and the Bernoulli distribution. So for example, the coefficient for each of the terms in the Bernoulli distribution, where it says n choose k, p to the k times 1 minus p to the n minus k. That's not going to be, well, that's a large, so p is probably a value that is between 0 and 1, right? Like n and k are integers, are natural numbers. It looks like p is just a probability.
Yeah.
Okay. Have you already done number 3, by the way?
I believe I have a solution for the most part. I believe it evolves for A, you have to model the quantum superposition. In that case, the teacher said you don't have to provide a general description, although I believe I kind of have. It for the quantum states, I'm not representing it, I believe, by sort of a proper mathematical notation as it would be, but it's more so in a sense a lot more general. So in that case, I'd say, let me annotate real quickly that the solution would be something similar to, say, square root of 1 minus p, like, to the n of, like, all states where k, where there are 0 ones, essentially. So I'll just note that as, say, of k equals 0 to represent that there are 0 ones. It's not proper, but it makes it simple. Then plus the square root of 1 minus p to the n minus 1 times p for all probabilities for all states that represent that have one in them. So I'll just write that as k equals 1 in that case, and then plus, and then I'll do dots to represent changing. So plus the square root of 1 minus p times p to the n minus 1 times all quantum states where there are n minus 1 k's in the quantum state. So k equals n minus 1. And then that's just going to be plus square root of p to the n, where there are n k's times all states where there are n ones in the quantum state. So I'll just write it as that pretty much. So that's what I was thinking. Oh, sorry.
Oh yeah. So the labels k equals 0 all the way up to k equals n, are those going to be the label of the ket state? So you're going to write the binary value of k.
What I was sort of planning to do is mostly just write it in term, just like hand write it, say like states, like just say instead of k equals 0, like states with 0 ones in them, and sort of from there, because I found it a little more challenging to write all possible states where, you know, k equals 1 and so forth. So I found that for the most part challenging, but ignoring that, this would be the general solution. I know the teacher though was fine with me just choosing general cases like n equals 1, n equals 2, n equals 3, and showing the different states and or possibilities for each. So
Okay, well, let me present sort of an alternative interpretation and sort of see how it fits in with yours, if that's okay. Would that be okay?
Yeah.
So you have a distribution which has an independent variable, and then which I'm taking to be k in this case, and then dependent variable, which is computed, or a function of k, which is going to be this coefficient. And so I don't know the shape of the binomial distribution. I'm just like drawing things randomly, but it's going to be discrete. So there's going to be a value for k equals 0 all the way up to k is n. And so that means the number of qubits that k would take, or n would take, is going to be, you know, like ceiling of log base 2 of n or k. And then your job is to make a quantum circuit that, well, classically you would compute what this weight was, and then you would compute, you know, deterministically a circuit where, you know, let's say starting in the ground state, starting with all zeros, the circuit finally puts it into a state where the weight on the first state is going to be, you know, the binary value of all zeros, and then the the final state where it's n is going to be all ones. So they're still going to be binary labels, just like you've been working on so far. Multi-qubit states on the computational basis have weights on labels. And so, yeah, that's my interpretation of it. You're computing classical weights, and then you're making a quantum circuit that applies those classical weights depending on which of these computational basis states you're operating on. And you can use, controlled knots. For example, like, all the ones in the label can be used as controls to enact some weight on that state that it wouldn't on other states where the label is 0 in that position. So, well, I'll pause there. And is this consistent with the way you've been viewing it, or is there a different way you've been thinking about it?
I think it was. This has I was thinking mostly that it would be viewed in a sense of that the number of qubits would simply just be n in a sense, because if n equals 2, there'd be sort of cases. That is what I was mostly thinking. I think that's what you were trying to say, and maybe I'm misinterpreting it, but yeah, I think that generally goes along the lines of what I was trying to say as well. So
Okay. So do you start in the all ground state, or do you start in some other state?
in this case, I believe that you generally start with kind of if I will scroll up real quickly, I believe I start with the Bernoulli state, which is merely a variation of the binomial state where n equals 1. In this case, I create more of a general format with n being equal to 1 essentially, and that for each gate, I figured that for each n qubits, you would apply an RY rotation of like 2 times arc sine of the square root of p to each qubit. In the original one, I just simply applied the NP 2 times arc sine of square root of p to all states, and I would get 1 minus p times the 0 state plus square root of 1 minus p times the 0 state plus the square root of p times the 1 state. I believe it would just be something as simple as applying it to all, like the RY rotation gate to all n qubits, but I may not be correct there. And with the same angle, I was thinking the angle would be the square root of p, but that's what I was at least, or no, not that was something, but yeah, that's what I was generally thinking.
Yeah, I think that general approach will work, but you might have to like factor out common rotations. Yeah, so okay, so this part C where it says, for the case of n equals 2, provide a quantum circuit that produces the quantum superposition that you did from part A and show that it is correct. So if n equals 2, then that means that the k is going to range from 0, 1, 2. And it says k is the number of ket ones in our quantum state with n qubits. Okay, so that's slightly different than the way I was thinking that. Yeah, so the number of qubits is n, like the way that you said, and they're treating the labels of the kets as the success outcomes. Like, in general, you have k, you have n trials, and then you have a distribution of k successes. And so for for the trial, you're taking a transcript of the trial run, and if there's like no successes, it was like a really terrible run. The probability of that happening is, according to your formula, n choose 0, p to the 0, which is 1 minus p to the n. And that's the weight for that, all the way to, if we take a random ket in the middle, like let's just say there's just one success, then the weight on that would be n choose 1, p to the 1, and then 1 minus p to the n minus 1, all the way to the all ones case, all n qubits are 1, which is the trial run where you have all successes, which is probably as equally unlikely as no success. Okay, I understand now, where p is the success probability in each trial. And okay, no, that part is making sense. So if you're comfortable with your solution for the binomial distribution, yeah, let's look at the discrete Gaussian and see if there's anything that would prevent us from doing something similar. I mean, like, first of all, see if I understand the discrete Gaussian. It looks like well, I'm reading the Wikipedia page. Is there a better page that you've been consulting for that distribution?
I think I've mostly been relying on the same page that you have been, but I believe I've also been looking at other different formulas. Like, I think there is this website from, where is it, the University of Michigan. I think they have a slide show on it essentially. So that's at least what I was looking at. So
yeah, can you send me a link to that one?
yeah, sure. So
yeah, and you can put it on in your screen share.
yeah, so here's at least the link I sent you, so you could use it on your own, but this
Great.
is sort of what they've been showing me. So they also include trapdoor functions, and it's very general, but they show strong trapdoors for lattices, and then I think they begin speaking about discrete Gaussians. So
Okay, it looks like they're showing this distribution on X taken over. Is that -1 to +1?
minus
can-
one. Let me see.
A
Oh,
little bit.
I think they're here. Yeah, this is just a positive one, the one-dimensional Gaussian function. Yeah.
But I mean, I guess like technically it's from -infinity to +infinity. And okay, well, this one is a continuous distribution. So I guess yeah, but lattices can also be infinite. I guess, yeah. Can you think of a way to map? So it won't exactly be this Gaussian distribution, but sort of like map it to the case that you have, which is going to, in general, be on n qubits. So it's going to be discretized.
That may come a little bit more difficult than expected, because I think I'm looking at the Gaussian distribution formula. I mean, if I look at this one-dimensional Gaussian function based on the equation on the left, the exponential, I believe, that means that.
Yeah, I mean, it could be,
Yes.
we could just clamp the distribution. Like, so for example, this distribution looks like it's centered on 0, and most of the weight is between, -1 and 1. And so we can just divide up that interval into two to the n buckets, like discretize it that way. And then for each of those buckets, you take the value of the probability distribution as the ceiling or the floor. You're rounding this exponential in some way. So I guess like to draw it, it might look like you have a distribution centered here, and then you sort of clamp it, wherever you choose that you think is wide enough, and then you're basically, for each bucket, you want there to be balance, so about 2 to the n over 2 on one side, 2 to the n over 2 on the other side. Then for each of these bars, you're computing a value which might look like ceiling of exponential of minus pi times x squared. Or, I call x sub I squared to show that the x sub i's are each bucket where I is taken from minus minus 2 to the n minus 1 to 2 to the n minus 1, and there's probably a off by 1 error because you want to include the xi including 0 as well, probably. And that's one mapping, but it has both negative and positive intervals. But then, when you have a ket label, it's going to be positive only. So you'll need to think of a way to map the coordinate of the buckets to a ket label that's always positive, and that's not hard to do. I mean, you can just shift up by half, so it's all positive. Like you can, when you compute the weights, you will treat the xi's as negative here, but then whenever you map it, when you're mapping it onto like which ket state it should be, you might be doing some transformation, which is like shifting it up by here so that all the bucket coordinates are positive, like greater than 0, to match with the ket states, so the weights match the label. So does that make sense? Like if you have, if this label you take as some value k, like a binary label, then to compute the weight that goes in front of it, it would be like rho of k, rho of k minus, your whatever shift you're using, which needs more space. So k minus 2 to the n over 2. Okay, so normally if you're allowed negative labels, you would just say, row of k, and sometimes the k's would be negative, but since we're required that all the k's be positive, then you're shifting it down by half. So that's why you're computing row of k minus 2 to the n minus 1. And that's going to be, this exponential function. So in your classical circuit, you would figure out what that value is for each of the k's. And then I think the reason why they were focusing on ry's from before is that on a block sphere, if you have purely real numbers, like let's say you're measuring real values on the point where states are in a superposition between ket 0 and ket 1, then you're kind of constrained in only a rotation that stays in the real plane. And so what axis stays on the x, it would be, a rotation along the y. So that's kind of, that y-axis is coming in and out of the plane. So intuitively, I think that's why the previous solution mentions like ry rotations only, is because using ry rotations, you can keep the probability weights completely in this real plane. So that when you measure it, you get back a real value, and the distribution of your measurement outcomes is going to match the distribution that you're trying to approximate, whether it's binomial or Bernoulli or this Gaussian distribution.
Okay.
And there are a few more details, like, they're talking about saying that the formula they gave you is for standard deviation of 1 over square root of 2 pi. And with mean of 0. Yeah, I guess you could make it easier on yourself. You could redefine the distribution that you want as not having a mean of 0, as you could have it being a mean of 2 to the n minus 1. But I'll leave that to you. I think that, yeah, it sounds doable, and it sounds like this is the general approach that you would take, and it sounds like the one that you're already taking with the binomial distribution.
Okay.
Yeah, do you have any, does that bring up any thoughts or questions from you? It's okay if nothing comes to mind now. If you think of any later, you can ask me over Wisant, and I'll take a stab at it.
Yeah, I think for the most part, yeah, I think I don't have any questions for now, but thank you for that analysis. That'll definitely be something I need to remember. So on that note, was there any other probability distributions in general that you found could be of interest? Or
yeah, it's a good question. So I mean, the one that is used a lot in quantum annealing or machine learning is this Boltzmann distribution. And so they have, in those problems, like in a purely classical setting, which is how people were solving it before there were quantum computers, there was an energy landscape, and there was like a loss function. And they were trying to explore the landscape usually with like gradient descents. They're trying to find parts in the landscape that would go downhill, and then they assume that if you go downhill, you're going towards a minimum. But sometimes you might get stuck in a local minimum, like, you know, the crater of a volcano is a local minimum. So you can like go down into the crater, but you're not actually in the valley of the landscape. You're still like stuck at a pretty high value. So to jiggle you out of this minimum, they sort of at every step apply this random, almost as if you were heating up particles on the landscape, so that they would jiggle and that would knock you out of these local minima. So if you're in a crater and you apply like heat, the state that you find can sort of jump out of the crater. And then if you're in the valley, even if you apply heat, you're at a pretty low, you're at close to the minimum. So you're not, applying heat isn't going to give you the wrong answer, if that makes sense. So let me look up to how so that's the Boltzmann distribution, is they apply heat according to a temperature, which is usually defined as T, and they increase the temperature on a schedule, and then they decrease it on a schedule. And if you do it at the right rate, you know, you'll knock yourselves out of these false minima, and then find the true global minima. And if you look at Wikipedia pages, yeah, let's start with just Boltzmann distributions. Yes, the probabilities are proportional to exponential of minus epsilon over KT, big T, where T is the temperature, you know, K is this constant to normalize it, but they often choose units where this K is 1. And so what are these epsilon i's? Oh, epsilon I is the energy of state I. So, okay. I'll share my screen briefly so you can see, and I'll stop your share if that's okay. You still with me, Caleb?
Yes.
Okay. So the distribution, the form is given here, and yeah, a lot of these symbols you can choose to normalize to 1. So usually K is 1, Q is 1, and so you're left with the probability that's normalized between 0 and 1, and the epsilon i's would be like your label K. So, you know, again, you have labels of all zeros, and then you're all the way to all ones. And so if we choose a typical state in the middle that has some mix of zeros and ones, and so dependent on this distribution is energy as a function of the state. So for particles, like for physical systems, the energy is like they measure it by nature, like, you know, for example, how many electrons are spin up versus spin down. But in your case, you do need to choose like this energy function, which is going to be the same as like a loss function. Well, that shouldn't rule it out, but that is like a more complicated step. For discrete Gaussian, you know, there's like fewer choices. So there's just one discrete Gaussian, and you choose it, and you can like shift it, normalize it. But here, I think we have to have a notion of energy. I mean, that's not so hard. There's, you know, like I mentioned before, let's say you have a system of particles on a line, sometimes called like an Ising system, and let's say it can be, usually it's like the particles that are spin up, down, and you can easily map a state that's spin up as being a 1 in that position, and then 1 being in a down. And then there's a coupling function that tells you like you're in a lower energy state if two neighboring particles next to each other either agree or disagree. And I forget which rule. I'm not a physicist, so I forgot which one of those is true, whether it's lower if like 2 electrons next to each other are spin down or spin up. I'm sure we could figure that out with ChatGPT as well. But the distribution would be 1D Ising model. Yeah, so here, if two neighboring spins are the same, they'll have a lower energy than if they were opposing spins. And you have like a long chain. And an analogy I think a friend used, which I think was like a really useful one, is that like, you're at a party or any kind of gathering, like, football game, convention, what have you. And then the people around you, like they could decide to leave or they could stay longer. And people are usually like socially influenced by those around them. So if everyone around you, if the 2 people next to you decide to leave the party, you might leave the party too. You're much more likely to leave the party. And if the 2 people around you are staying at the party, you're more likely to stay at the party. So those are kind of like the 2 kinds of spins. And it's not uniform. You can imagine this, if this party is a strange kind of party, it's on 1D, there are clumps of people who are like staying or not staying. So clumps of particles that are spin up or spin down, but it's at the boundaries where, you could have particles flip their state and there are n particles on this field, let's say. And so is there kind of a low energy, is there a stable solution? Yeah. What are the stable solutions of it? And here is where the Boltzmann distribution appears. And the Boltzmann distribution, is just like a generic family of distributions that are parameterized by this energy function. So H here stands for Hamiltonian, but in physics, it's just the operator that gives you the energy. And so this has a big P, but you can treat it as like the probability of little p. And then before on the other page where you had epsilon sub I being like the energy of state I, now you can just have it be this energy function. So if you had I'm using K as just sort of the label of the ket state. And so if you have a sum over all pairs of neighboring particles on this line, you have some constant, which I think for simplicity, you may choose like all the J's to be uniform weight, which would be the case is like, you're at the party and everyone sort of has equal social influence, or, it's a very democratic party. So all the pairs of particle are equally considered. There's not like one person who's more popular than another. I don't know if that's like really realistic, but it could be. And then you have sigma I and sigma J. And in this formula, the sigmas are taken from +1, -1. If you read up above, slightly. So and in your ket labels, they are going to be 0 and 1. So, there are tricks to convert from 0, 1 random variables to -1, +1 variables. I think in the direction that we want to go, which is from 0, 1 to -1, +1, it's going to be like 2ki -1, I think. Yeah. So if you have a 0, 1 variable and you want to convert it to a -1 +1 variable, you just double it and subtract 1. Yeah, I think that's it. So okay, and so that's the amount of the term that you want to say this is low energy if they are if neighboring pairs are in the same state. And then there's also like a weight. So this mu, which I'm leaving off for now, is whatever weight each individual particle has. Like some positions, some particles may have some contribution to the energy of the overall state differently than the others. I can't think of a good example, but this is the most general form, and you don't have to choose it. And you can also, I guess, like read about physically realistic examples that this might be useful for. Like, for example, an old term, I guess the original example of this Ising distribution was this ferromagnetism problem. And I think it appears like old computer hard drives used to be magnetized, and it would be like tiny iron filings. And if they were all aligned in the same direction, it doesn't matter if it was like, east versus west, but if they were all aligned in one direction, that was a low energy state. And it would tend to stay, it would be stable because, you would leave the hard drive, you could power it off. And the next time you powered it on, it would stay mostly in the same place, unless, if you watch really old movies, you could mess it up by running a magnet and scrambling all the positions. And really old credit cards also have this, I think credit cards also have this problem where they encoded digits on this magnetic strip, and you can also ruin them by running a magnet, but it's exactly the same. And some of them are rewritable. And so that might be interesting to you, is that there's a physical example which is behind this Boltzmann distribution. And this kind of tells you that yeah, I think if you increase the number of particles in this state enough, that will give you like a really big energy difference. And then, that might be how you design your system, like your magnetic strip or your magnetic hard drive is like you say that you want there to be a 1 in 1 million chance that all the bits flip from one state to another, because you want it to be like a really reliable storage device. Well, I'll stop there. So that's like a lot of me talking. But if it's interesting to you, I would encourage you to sort of pursue this direction.
Okay. Yeah. Thank you so much for that. So anyways, I think that's mostly all the questions I've had for the problem, but yeah, if there's anything else you'd like to talk about, feel free to talk about it.
Yeah, well, I mean, the problems I think are very interesting in general. And, I was thinking that if there were, afterwards, if you wanted more quantum problems, if these were not enough for you, I actually had a student give me a kind of an interesting, more algorithmic problem. So kind of like on the line of Shor's algorithm, which is how to break crypto systems, which I don't know if you'll get to in the summer session. And this problem is called Deutsch's algorithm, and it's it's very similar to solving like whether you're given an even number of like 2 out of 3 ones or all zeros. So yeah, it might take me a while to find it, but I guess the more standard name is called GHZ, both the problem and the algorithm that solves the problem. And you might like it too. So it's you're given this promise, and the promise is that your input is balanced, like either half zeros and half ones, or it's all zeros. And I won't ruin it by showing you the circuit that solves it.
No, that's definitely sounds interesting. If I could have like a look at the problem itself, that'd be definitely incredible.
Yeah. Okay. So I misstated it slightly. So you're given an oracle, a black box that implements, purely classical function. It just takes, n qubits to an output 0 or 1. So it's a Boolean function, and it's either constant, so it either outputs zeros at all locations or 1 at all locations, or it's balanced, which is just, half on half the inputs it returns 0, and on half the inputs it returns 1. And it's very similar to the guessing game in that classically you would have some probability, like if you sample it in n places, and if you find that it always returns the same value, then you have so high probability of guessing constant. But the more you sample, and the more likely you are to discover the place where it's balanced. Like, maybe you got all zeros, and then you only have to receive 1 1 to know that it's the balanced kind and not the constant kind. So I'll send you a link to this problem too. And also put it in the learning log. So if you run out of, or if you get stuck, or you get tired of thinking about the probability distribution problem and just like want to switch tacks, GHZ is a cool problem to think about. And I think you have all the tools, like, everything you use to solve the guessing game with the GHZ state that you have would be useful, and also in GHZ.
Okay. Thank you very much for that. Anything else, or is that like about it?
Well, it's something else might come up, but yeah, I think that might be enough for now, and I'll keep my mind open. There are other cool problems that we can talk about next time. About quantum. It might be, I'll read like what actually Anton Zeilinger got the Nobel Prize for this year, because he is the Z in the GHZ state, but I'm sure that it was much more than just studying that state that got him the Nobel Prize. So maybe I'll look into that, and if it's something that I think is suitable for our next session, I'll prepare something about that.
All righty. Thank you so much for all of your help, and have a great rest of your day.
Yeah, you too. Bye, Caleb.